Okay, so let's continue with problem 8 on page 272 in the text, which now is, if you look up here, it's page 277 in the PDF, but it's labeled page 272. Well, what's the sample space size? Well, we're tossing a coin twice, so it's going to be, you can have heads or tails on the first one, heads or tails on the second one. So the sample space size is equal to 4 because 2 times 2, those are independent events. Now, if we label the events with the 2 letters, then the sample space itself is going to equal So there's a representation of the 4 outcomes that compose the sample space, and it has 4 outcomes. Okay, now let's go on to question 9, which is what this is set up is on the next page, 273 or 278 in the PDF. Number 9, the first one says, concerning the same probability experiment, define the event EH to include all outcomes in which a head is showing. So what you want to do is write down the definition of the event in which one head is showing. I'm going to, okay, well, let's see. We want to have all of the outcomes here that have a head showing, at least one head. So there it is. E head is these 3 events. Okay, and then you want to know what is the probability of this event here. And it's asking for 2 things: a formula, and then it's going to be a ratio. It's going to be a fraction in both cases. Here's a formula, and here is the 2 numbers. So let's take a moment, and I'll give you can pause the recording, pause your playback, that is, or out this. Okay, well, the probability of this event is going to be, well, what I mean by the formula is just the definition of the number of elements, number of outcomes in the event divided by the number of outcomes in the sample space. And so it's a fraction, and these are 2 integers. And what I mean by 2 numbers is, let's figure out how many numbers are in each of these sets. Well, in this set, you can see that there's 3, and in this set there's 4, because we're dealing with this sample space. So that's the answer. The probability that you have heads, at least one head, is 3/4. And so the same thing you can see, this just for practice with tails. Oh, for if it was this would be the same thing if you had the if your experiment was, or you were looking at a family that has 2 children, and you ask, what's the probability that you say have at least one girl, then that's going to be 3/4, because that it's going to work the same way and that'll okay. So you can apply the same model to different concrete situations. And then there's some probabilities here of these different sets, the unions and the intersections. Okay, that's basically this is sort of the basic sort of stuff with probability, is just the stuff we've gone over. And so we can next time, and we stay with probability for 2 weeks, because there's a second sort of topic, which is relations between events, when you have the ideas of conditional probability, which is important, but also subtle and difficult to understand why it's the case. And as an example, that there is, let me describe what's called the Monty Hall puzzle, which requires some tools that we don't have yet. And so this is a person's name. There was um, a, a game show on, I think in the last, in the 1970s and early 80s. I think it's called Let's Make a Deal. Anyway, the MC, the host, was named Monty Hall. And so the game was, you had, say, a contestant, and the contestant could choose, well, the contestant was presented with, say, three curtains or three choices, and they could choose any which, and behind one of them would be a prize, like a car or $1 million, and there were joke prizes behind the other ones, like a bar of soap or a goat or something like that, something that would be relatively unappealing and relative to at least to $1 million or a new car. Okay, so the idea was that the contestant would choose one. Let's say they had no information. It was just like, and there was no, rhyme or reason to which curtain it was behind. And so they would choose, let's say they would choose one. Let's say they choose a curtain or option 2. Well, then what Monty Hall would do is he'd open one of the curtains that the person didn't choose. So for example, here, what you'd see is that you'd see here, like a bar of soap behind number 1. So this would be opened. So Monty Hall opens one non-valuable curtain, and then asks the contestant, and this is what makes the game at least somewhat interesting, is, do you want to stick with your original choice of 2 or switch to the other one? So the question is, for the contestant, stay put or switch? Now, for the whole length of this show, when it was running, it looked like, well, if one was opened, it looked like there was 2 or 3, and you didn't have any information about what was behind what window. It looked like it didn't matter whether you stayed put or switched or not. So, and the game people thought this, so that they thought that it wouldn't matter, so they had sort of figured into their how many prizes they'd have to hand out would be that half the time the person would be correct, no matter whether they stayed put or switched, and half the time they'd be incorrect. And so this was actually a pretty good deal for the contestant. It's like much better than a lottery, that you actually have, like, I mean, even the beginning choice, you've got 1/3 of a chance that you've got $1 million or a new car. I mean, that's a pretty good odds. And then, so the question was, what makes it interesting for probability is the probability of these two, I mean, you haven't done anything. You've just seen this has been opened. Should you switch or stay put? Is the probability of winning the same or different? Now, this has been a well-publicized puzzle, so you may know the answer. But the question is, do you even if you know what the answer is, do you understand why that's the answer? And the connection here is that it's a connection between different events. You have sort of like, well, the prize could be behind window 1, window 2, window 3, and it doesn't matter whether like it was actually randomly distributed. Like the producers could really like window 2 or window 3, and it wouldn't matter. So, but let's say that it's equally likely to be behind any of the 3 curtains. As far as the contestant knows, that's true, and that actually doesn't matter in this larger scheme of things, whether the probabilities were classical or not. But the issue is that something really is going on here, because it turns out that the probabilities aren't equal between these two. And it's sort of like, now, if someone walked in off the street at this point and made a choice between, and all they had was these 2 curtains and this was open, then they're and they didn't know what had happened, well, then their chance of getting the prize right would be one half, it'd be 50%. But this person knows something that the other person didn't. And that connection between the events means that their probability of which strategy they should choose, one of these strategies gives you better chances of winning than the other. And you could extend this puzzle to, what if you have a 4 curtain puzzle or a 5 curtain puzzle? So there's extensions of this. You really want to understand how it works. So if you were confronted with a 4 person puzzle, then that would make a difference. Okay, so this is what we will do, look at. And the second one, at the end of the chapter, there's something called the purple probability puzzle. And this again involves what are called conditional probabilities. And so what is this? Well, this is the case that you have 2 jars. And the experiment that you're going to carry out is, first of all, you have 50, I think, red and 50 purple marbles. And the idea is you can distribute them any way you want. And the goal is, what you're going to do then is choose one of the jars and then pick out, have someone choose one of the jars and pick out, randomly pick one of the jars, and then randomly pick out, they blindly have to pick one of the jars, and they blindly pick one of the marbles from the jar. And the goal is you want to distribute these in these 2 jars so that you maximize the probability that you get a purple marble. So that's the other one, that to understand, then figure out what's the probability of getting a purple marble. And that is, again, a conditional probability puzzle. Now there's a puzzle that just has to do with our classical one, which is the following: is if you like in our class, if we have, like, say 13 students, the question is, what's the probability that 2 of us have a birthday on the same day of the year? And that's a counting problem. So we can deal with that puzzle also. Will, you have a question?
Yeah. Before we move on to another puzzle, would it be better to put all of the color marbles in one jar and all of the other color marbles in the other jar so
Well,
that it's
well,
50?
so that's the idea. That's one choice. Let's say you put 50 red and 50 purple. I've forgotten now if they're purple or blue or whatever. Okay, well then, so then the issue is that we have to deal with the fact that what we first do is choose a jar randomly, which is 1/2, right? If it's equally likely to choose the left jar and the right jar. But then if you choose the left jar, the probability of getting, if you just pick one out of this red jar, then you sort of think, well, there's no chance at all that you're going to get a purple one over here, was 100% chance over here. So what's going to happen is that the chances of you getting a purple marble are just going to be, did I choose the right jar? So it's going to end up being 1/2, 1/2. Now we have to understand this in terms of conditional probability. So this is going to give you the probability of 1/2, 1/2, but you can do better than that. So this is not the best distribution.
So it would be
So let's not,
25. Oh, okay.
that's the experiment. So what you want to do is you want to go and think about it over. Everyone can think about this, and we'll come back, because we want to not only sort of come up with, so you may be able to come up by sort of intuitively coming up with the right answer. And so everyone can probably, instead of us all trying it right now. Why don't you think of it for next time and for next week, because we're going to deal with some of these puzzles next week, and that's the, but then these are all in the, if you look at the end of, we have to first deal with conditional probability and that issues, but then if you look at the end of the chapter for probability, oh, I don't want to go, I want to stay here, that you see what we've covered here is essentially the first 4 sections. And we have this last section here, which has to do with connections between events. And then we have the law of total probability. And then here's some probability puzzles. Here's the Monty Hall puzzle. And so they're like, the first one is the birthday problem, which is given a certain group, what's the probability that 2 people have the same birthday? It turns out that it's like becomes, even if you have a small number of people, the probability rapidly gets really large. So that's this first problem here, the birthday puzzle. And we can, there's some other puzzles here to do with probabilities. And then here's the one that we just did is sort of this project of the, here's a description of that purple probability puzzle with the 50 purple marbles and 50 red marbles. And then we have the Monty Hall puzzle. And here's what the game show looked like in the 1970s, which 63 to 77. And we're almost out of time, but let me just comment on there's a letter here that was written from Monty Hall to Lawrence Dennenberg, who he's actually now the dean of the computer science department at Harvard University now, and he teaches discrete math, which is the version of this course. So you can take anyway. He's still teaching discrete math, and here what he wrote to Dennenberg, saying, in sending my okay for use of Monty Hall. So I guess he had written and wanted to be able to get permission to use, I think in his course, the Monty Hall paradox. It says, he wants to ask you a question. You mentioned part A, the player should switch doors even without additional compensation and be paid to do it. And so he goes through the argument and says, but as I see it, it wouldn't make any difference after the player has selected door A and having been shown door C. Why should he then attempt to switch to door B? This sort of gives away the answer, but not why. The major prize could only be in one of the 3 doors. He's made his selection, and then there's only, so he says it shouldn't make a difference. And that's shows, but the thing is, this made a big difference for the TV show, because that meant that if the people had understood in the Monty Hall puzzle what was actually going on, there would have been no hesitation of what their strategy, and the game show would have lost a lot of its, it would have lost more money and lost a lot of its interest. So it was just an interesting situation. So that's why this letter is up here, is connected to the Monty Hall puzzle.
Thank you, Professor.